Thank you, and everyone, and welcome to the session. I am honored to be co-hosting this session of the International IVF Initiative. Before we get started, we do have a couple of housekeeping reminders. If you are interested in any videos from previous sessions, please go to ivfmeeting.com and you can find all of the previous recordings. And we would love it if you could leave a review as well. Also, during this session, we would be very excited for you to ask any questions. Please do so in the Q&A section of the Zoom feature instead of the chat. So questions go in the Q&A, not in the chat. Thank you. So let's get started. I'm Alison Bartolucci, and it is an incredible honor to be co-moderating the session with the distinguished Professor Catherine Racowsky. As most of you know, Dr. Racowsky is the immediate past president of ASRM and past associate editor of Fertility and Sterility and Human Reproduction. Her accomplishments and contributions to this field are endless and still ongoing, and really just a few of them can be found in her full bio on our website, so I encourage everyone to check it out. And now, while she's currently living her best life in France, where she is a university consultant, Dr. Racowsky is also a professor emerita at Harvard Medical School. And it is here where she was the IVF lab director at Brigham and Women's Hospital for over 20 years. And this is where I met Dr. Racowsky and was lucky enough to be trained by her and truly inspired by her to pursue this as my career. She has been a mentor and model of strong female leadership through the years, and I couldn't be more excited to be with her today. Catherine?
Boy, Alison, thank you so much. It is my pleasure and honor to be co-moderating this session with you. It's really unbelievable to think that we've known each other for more than 20 years. It's truly unbelievable. And at that time, 20 years ago, when you told me that you were thinking of not being a veterinary student, but actually joining clinical embryology, of course, I was absolutely thrilled. So here we are co-moderating together. So Dr. Bartolucci is just recently obtained her PhD. She is the Director of Laboratory Operations at the Center for Advanced Reproductive Services at the University of Connecticut. She received both her master's and her PhD in clinical embryology and andrology, and her PhD in clinical reproductive sciences from Eastern Virginia Medical School. Alison has served on the SART Executive Council as the SRBT laboratory representative for 3 years, from 2014 to 2017. She has also been an invited speaker at multiple conferences across the country, and has numerous first or co-authored papers, peer-reviewed papers of one sort or another. But I think her real specific interests are in oocyte and somatic cell communication, which of course is one of my loves as well, Alison. And in addition to that, embryology and optimizing quality in the clinical IVF lab. So again, it's a real pleasure to be here co-moderating with you. And if you want to learn more about Alison, please go to the website. So, as you are no doubt aware, this session is entitled, as Alison mentioned, Cryogovernance Iii, and it concludes our series looking at best practices in cryo storage and handling frozen gametes and embryos in the clinical IVF world. Tonight we have 3 fabulous speakers, and we're going to be looking at some of the unknowns. How much handling of vitrified samples is detrimental to survival? How to be complete in your risk assessments in storing samples at your facilities, and finally, the difficult topic of how to maintain and clean your dewars and dry shippers. So, Alison, without further ado, I will turn the podium back to you.
Thank you so much, Catherine. So our first speaker is Dr. Vicky Santos. Dr. Santos is a researcher at the National Scientific and Technical Research Council at IPATEC in Argentina. She specializes in numerical simulation using the principles of thermodynamics to create models that can be applied to both food engineering and cryopreservation of biological materials. She has co-authored 2 publications on the implications of storage and handling conditions on vitrification outcomes, as well as the use of mathematical models to predict the development of vitrified warmed oocytes and embryos according to their cooling and warming rates during storage and during removal. She is here to discuss these topics with us today. I want to warn you all, that all of you fellow math phobes, that she is going to be presenting a lot of math, but you can do it. Hang in there, because there is she packs a big punch at the end. So without further ado, I'd like to share the pre-recorded video. Vicky is here with us today, but her video is pre-recorded.
About our work regarding the storage and handling of vitrified materials. I want to tell you that I am a chemical engineer and my PhD was also in engineering. So I want to invite everybody to think like an engineer when handling vitrified samples. I have developed several numerical models to simulate processes in food engineering, which I later applied to the reproductive area in order to determine cooling and warming rates of cryobiological systems. In the field of cryobiology, I have also studied the cryopreservation of seeds, and now I am in a preliminary stage doing some research in cryopreservation of recalcitrant yeast that are of biotechnological importance, and the cryopreservation of rainbow trout semen of a specific strain that has thermally adapted to higher temperatures. Also, Marina Sancinena, which is a co-author, she has achieved the vitrification of equine oocytes that have been successful, since you can see in the slides her 2 6-month-old foals, and the oocytes were named Tango and Milonga. I work in the National Scientific and Technical Research Council in Argentina, and all the authors are currently living in Argentina. It's at the tip of the Southern Hemisphere, and it's a country with a great diversity, since we have ice glaciers, and up north we have the Iguazu Falls, which is the largest waterfall system. We are a very heterogeneous group. Dr. Sariski and I, we are both chemical engineers. Dr. Chirife is a food scientist, and Dr. Marina Sancinena, she is our specialist in the reproductive area. Okay, so we have no conflict of interest in all our research articles. Okay, so everybody knows what happens to samples when they are frozen slowly, and when they are frozen at high cooling rates. So I'm just going to dive into the vitrification and tell you something about it. The vitrification is important to cryobiology because the natural state of liquid water inside living things is disordered. Therefore, when we vitrify, we maintain this natural disorder as the sample solidifies. How do we do this? Well, we have a supercooled solution that when it's cooled very quickly, the viscosity may reach values that are very, very high. So if we do it quickly, we do not allow the molecular rearrangement into a crystal structure. Therefore, we avoid the ice crystallization. It is a second order phase transition since there is no latent heat involved. The glass transition point, the TG, is the temperature where there is a reversible transition from an amorphous solid or glass into a viscous or rubbery state as the temperature increases. Below TG, the materials are rigid and brittle and amorphous. So what can happen to a vitrified sample during warming? Well, it can suffer devitrification. This is a phenomenon where there is ice formed during the warming stage. And also we have a recrystallization, which is the conversion of many small ice crystals into larger ones. These two phenomena occur at different temperatures and at different rates. The ice nucleation rate, for example, is high near the TG of the sample, and the ice growth rate is high just below the melting temperature, So what are the minimum rates? The lower the concentration of the cryoprotectant, the faster you need to cool in order to avoid ice formation. And the minimum cooling rate necessary to avoid the significant ice formation is the critical cooling rate. The minimum warming rate in order to avoid the vitrification of a vitreous sample is called the critical warming rate. The critical warming rates are typically 2 or more orders of magnitude greater than the critical cooling rates. So if you have successfully vitrified your cell, it can devitrify during warming to form small intracellular crystals above Tg. And as the temperature increases, then these small ice crystals can grow in size by recrystallization, and that could be lethal. Fast warming is critical. This is a point often overlooked during the cryopreservation of reproductive cells. As you can see in this figure, the critical warming rate are higher than the critical cooling rate. They are 2 or more orders of magnitude greater than the cooling rates in order to avoid the vitrification and survival of cells. This was also published and said by Peter Masur and Seki in this paper, research paper, where they stated that this is a new paradigm for the cryopreservation by vitrification. Because before, everybody was focused on cooling very fast, getting this vitrified sample, but now you have to focus on the warming because, as you can see, it's more critical. When can warming occur in a vitrified sample? Well, it can warm while we check before and after a transport from clinic to clinic. While we are doing witness step in IVF, and another embryologist has to check the ID of the sample. While we are transporting vitrified samples in dry shippers, for example, there is no liquid nitrogen allowed in airplanes. So these are steps where it's too hot to handle slowly. You have to be efficient, you have to move fast so you don't expose your straw, your sample, or your cryo device to high temperatures. And you have to be careful by monitoring the entire thermal history during the cold chain. So, since penguins are always present in a presentation in vitrification, I had to put mine in. But I have to say, we have to move with a rocket speed when we leave the liquid nitrogen to warm very fast, because warming is critical. So Marina Sancinena told us when we were in our group, we have to focus on the warming. What happens to the samples when they are handled in the storage in Dewars? And it's very difficult to measure the temperature in cryo devices because we have very minimal volumes and they are very small in size. It's very difficult to put a thermocouple and measure time, temperature versus time. And you can observe a sample while it's crystals are forming during cooling or during recrystallization and fractures using cryostereoscope. But you can't do that every time you are going to vitrify a sample. So that's impractical and you are prone to high experimental errors. So what are the alternatives? Well, we can predict time temperature curves by numerical modeling of the heat transfer in these cryo devices. And we did that in our group, but we did it for cooling rates first. So we found the performance of each cryo device for cryotip, cryotop, cryoloop, etc. And we found the cooling rate and the performance for each of these devices. After 2013, we said, let's use these numerical models and try to see the warming of these cryo devices. But therefore, we applied the numerical methods to cryotop and to OPS. And that's where we're going to focus. Our objective was to find the glass transition temperature of a vitrification solution. and to describe the devitrification thresholds and how they affect the storage and handling conditions of vitrified samples. How did we do this? Well, we first measured the TG using differential scanning calorimetry, and we used mathematical modeling to predict the time temperature curves and the devitrification threshold during warming of OPS. This was done using the numerical method called the finite element technique. And we did it in a software called COMSOL Multiphysics. So we solved the partial differential equation to describe the heat conduction process of OPS when we lifted the OPS from the liquid nitrogen and maintained it in a nitrogen vapor phase. We also measured the temperature inside a cryogenic storage dewar, and when we disturbed the nitrogen vapor by raising and lowering the canister. Here we have a diagram of the heat flow versus temperature and the key thermal transitions during the vitrification of a sample, or of a vitrification solution, I mean. We use a differential scanning calorimeter, and we can see here that the step change is the glass transition. The onset of the vitrification is TD, and it has an exothermic peak. And then we have the onset of melting with the endothermic process. Here we have the actual curved thermogram for our vitrification solution. You can see we have the glass at -125 approximately, and the devitrification peak and the melting or diffusion. And we could calculate the heat of the vitrification and the latent heat of melting. Well, here are the heat transfer equations for the OPS device. I am very sorry for everybody, but I am going to show you the equations, the governing partial differential heat transfer equations for this bidimensional axial symmetric domain, because it took me about 5 years of PhD to understand, solve, and find and achieve the prediction of the temperature inside these devices by solving all these equations. They are very complex. We need a lot of time, and well, it took me 5 years that I can resume here in one slide. Subscript F and P are the biological and the plastic support, and we have to know that there are thermophysical properties involved in these equations, which are the density, the specific heat, and the thermal conductivity that must be known and used as input information in the numerical model. If we solve all these equations that are second-order derivatives and in transient state, we can find the temperature as a function of radial and axial coordinates and time at each point inside the device. So the OPS system, we have 2 volumes, 1 microliter and 2 microliters, and we calculated the length over the diameter, and it was 2.4 for 1 microliter and 4.9 for 2 microliters. So this cannot be approximated as an infinite cylinder. We had to use a model where it was a finite cylinder. And an important aspect of the equations is that we need the boundary equation. The boundary equation involves the use of the surface heat transfer coefficient, which is a very important engineer parameter. It is a characteristic parameter of the convective heat transfer between the fluid medium and the surface of the object that is being cooled or warmed by this fluid, which surrounds the entire object. The H appears as a proportionality factor in the equation. Here you can see H times the temperature of the surface minus the external temperature. The temperature of the surface is the surface of the object, the OPS or the cryotop, and the external temperature would be the temperature of the nitrogen vapors. And that, as you know, we have liquid nitrogen at -196, and as we move in a vertical direction, we have an increasing temperature gradient of nitrogen vapors. What we have in a Dewar tank is a stratification phenomenon of the nitrogen vapors. The top of the Dewar represents the hot surface, and the liquid nitrogen would be the cold source. So when you have a hot surface facing down, you have a stratification phenomenon because the density decreases with increasing temperature. So the less dense layers are above the more denser ones, and therefore there is no convection, and the heat is transported by conduction only. This fact means that the H are decrease in value in comparison to the opposite, for example, for a heated pot where the cold source is facing up. So what do we need in the numerical model? We need the heat transfer coefficients that we have determined in our group, and we also corroborated these values with literature values using the Nusselt correlations. And we selected and calculate they were between 10 and 15 watt over square meter degree Kelvin. We selected two different nitrogen vapor temperatures, -70 and -50 degrees, and they were considered for the calculation of the critical time needed for the system to reach a final temperature that would be -100, -120, or -130. These are values close to the TG of the biological fluid. The initial condition, well, it was submerged in the liquid nitrogen. It was -196 degrees at times at T equals 0 seconds. And we have the thermal properties of the plastic and the thermal properties of the glassy water. All of these properties are involved in the governing heat conduction equations. Here you can see the temperature at different heights measured from the top of the Dewar. For a full Dewar, you can see that at 14 centimeters, you have reached temperatures above TG. And for a half full Dewar, there is also almost 2 centimeters away that reach -125. That would be around the TG of our vitrification solution. So above, we have risky zones that can enter, the sample can enter a rubbery state. What happens if we disturb all this nitrogen vapor in a half full Dewar? Well, we reach the TG at about 26 centimeters. That would be point B in the Dewar, below the neck. This is another way of showing these results, that for a full or half full, we have the dangerous zone here at the neck between 14 and 16 centimeters. High risk of the vitrification since the temperature here of the nitrogen vapors are above TG. And for a half full after raising, we have a larger zone that goes to about 26 centimeters. So we know that the OPS, when it's placed over a certain height above the liquid nitrogen, it begins warming. And as the height increases, the temperature of the nitrogen vapor also increases. So if the OPS reaches the TG, the vitreous biological sample may enter into a rubbery state. It transitions into the state, and it would then have the ability to form ice through devitrification. How do we quantify this time? How much time do we have? Well, we can quantify this critical time using numerical modeling of the warming process, using, as I said, the software console with the finite element method. And here you have the figure where we have predicted the temperature versus time in the OPS at a critical point, which is and it tells us that minus 120 is reached at about 54 seconds for an H equals to 10 watt over square meter degree Kelvin and a nitrogen vapor temperature of minus 50. We made several predictions for different temperatures and two different H values. And these are the times in seconds of these critical times that are very important to know when we lift samples. So the results tell us there is a temperature distribution of nitrogen vapor inside a Dewar that is non-uniform. And it's because we have a stratification phenomenon of these nitrogen vapor layers. These temperature gradients are similar in a full and half full Dewar. However, when we disturb the nitrogen vapor, we establish a new actual distribution of temperatures, and we have higher temperatures overall. The nitrogen vapor temperature established after these disturbance is a critical value because we increase the risk of damage to vitrified samples. The mathematical modeling tells us that an OPS could reach a devitrification temperature in about 30 seconds when exposed to minus 100 to minus 130 degrees Celsius. Well, we also measured the TG, and it was in the range of minus 126 through to minus 121, after which, if we increase, we enter rubbery state and then devitrify. In this medium, cells should be stored at temperatures below minus 121 degrees Celsius or lower. And because storage under rubbery conditions is unstable, samples should be handled and stored below their TG. Now we wanted to test the survival of bovine oocytes during handling in Dewars. And we applied 3 treatments. A one-step removal from liquid nitrogen. Treatment 2, a one-step removal from nitrogen vapor. And treatment 3, it was a 2-step removal with a 15-second pause at the Dewar neck. We can see here the effect of the 2-step removal from a vapor, a nitrogen storage. The temperature here was above the TG, and the hatch at day 9 gave a survival of 0. So the other 2 treatments, which were samples exposed to temperatures below TG, there were no significant differences, and there was survival. Final results. There were no difference in development vitrified warm oocytes after one-step removal conditions, either with samples submerged or stored in nitrogen vapor. These results agreed with the recommendations previously proposed with the numerical models that the sample should remain below TG. In contrast, with 2-step removal condition from nitrogen vapor phase, the temperature of the sample surpassed the TG and the survival was reduced. Under these conditions, the samples were exposed to temperatures shown to be in the range of the rubbery and devitrification thresholds. These results, therefore, reinforce the importance of exercising extreme cautions while handling vitrified material during routine laboratory procedures, such as identification and confirmation and inventory keeping. Final remarks. Storage of vitrified samples in liquid nitrogen vapor phase constitutes a potential risk since devitrification can occur if we disturb these nitrogen vapor layers. Devitrification thresholds should not be interpreted as a fixed value since it is influenced by the TG of the media and the heat transfer efficiency of the vitrification support, because it's not the same if we have a cryotop or we have an OPS or a cryolief or any other vitrification device that has different loaded volume in it or different thickness in the plastic supports. The mathematical modeling can be used to analyze complex thermal phenomena. It can be applied to evaluate the critical warming times, new storage conditions, new storage designs, and inventory procedures prior to exposing real-life samples. Well, thank you all for your attention and here we have the references.
Well, Vicky, thank you so much for that fascinating presentation. I'm quite sure we've all been wondering about these rather dramatic changes in temperature fluctuations when handling vitrified specimens, both in the vitrification process and also in the warming process. So really appreciate your presentation. Thank you so, so much. So I have a question for you, and this relates to the cooling rates of various cryo devices. So please don't mention names, because we don't want to black name any particular manufacturer. But the question from the audience has been, do you know what the different cooling rates are for the different cryo devices? What the differences might be? And again, please don't mention any names. And the obvious underlying reason for this question is that we all are trying all the time to use the best possible equipment and devices for handling our patients' embryos and gametes.
Okay. Yes, the cooling or the warming depends on several factors, which I mentioned some in the slide. They depend on the volume that you load, how it is distributed, how is the geometry, and where it is contained, the plastic support, the thickness of the plastic, if it has another plastic inside, or if you put it in another straw, because these things create resistances to the heat transfer. Therefore, when you have a direct contact with the liquid nitrogen, you have a certain velocity that could be much higher than if you don't have direct contact, or the volume, if you load different volumes. That's why we use the numerical models to avoid the variations due to the handling of a person with the different volumes.
Sure.
The numerical model, you can put 0.1 microliters or 1 microliter, and you compare that.
Right. I guess the question though is, and I don't want to spend a lot of time on this, but the question is, if you control all those variables, do you see differences in cooling rates that might be of concern while we're vitrifying ourselves? I think that's,
Yes.
From a clinical, practical perspective, that's probably the underlying reason for the question.
Yes, there is differences in cooling rates and warming rates, which are critical.
Yeah.
From my perspective, they are more critical because yes, the volume and the probability of forming ice depends also on the volume of the sample. So
terrific. Thank you. Well, we're going to move on. Thank you so much. I'm sure you'll get other questions during the Q&A session. So thank you. Okay. So now we're going to turn to our next speaker, Dr. Kristen Ivani. And so Kristen, it's a very great pleasure to introduce you. You have completed both your BS and master's degrees in animal science with an emphasis in reproductive physiology. She then went on to earn her PhD degree in physiology in the Animal Reproduction and Biotechnology group at Colorado State University. Kristen served as the IVF laboratory director at the Reproductive Science Center of the San Francisco Bay Area in San Ramon, California for over 30 years, before recently turning over the reins and being promoted to part-time embryologist and consultant. So Kristen will be giving her presentation entitled FMEA, a qualitative and systematic tool for cryogovernance. So Kristen, welcome to the podium.
Excuse me. Thank you very much, Catherine and Alison. I would like to thank the I3 group not only for the opportunity to speak with you today, but also for the amazing work that you've done for the last 13 months or so, bringing us incredible presentations from around the globe that are relevant, fun, and very interesting. So my talk today, we're going to discuss failure mode and effects analysis, FMEA, specifically as it applies to cryopreservation. When I got here, I had nothing to disclose. However, I would like to disclose that it's a pretty tough act to follow after Dr. Santos, so I will do my best. So FMEA originated in the 40s in the military, and it's a collaborative step-by-step approach that we can use to identify any and all possible failures in a design, manufacturing process, in a product, or with a service. And there are two main components to conducting an FMEA. First, the failure mode, or all the ways that something might fail. And the second part is the effects analysis, where we study the actual consequences of those failures. It's important to note that this is a proactive risk management tool that uses process mapping to identify, eliminate, and reduce failures, and thus reducing our risk as low as possible. And this would be in contrast to something like a root cause analysis, which is generally done after some type of failure. So this is a proactive step. Some of the benefits of FMEA, as I mentioned, this is a positive approach to mitigate risk, which makes this oftentimes a lot more attractive of a program to embrace because it is looking forward. We're able to improve our processes, and it also improves collaboration between all the involved parties. So when would we perform an FMEA? It's really four times that we would do this. When we're designing a new process, when we're setting new goals for an existing process, when we're applying a product or process in a new way. For example, if we're going to use a new cryo device to vitrify eggs after previously only using it for embryos. And finally, when we're assessing a failure or a malfunction in a process or a product. And this is a very involved multi-step process. So let's just go by this step by step, how we would conduct an FMEA. First is you want to identify your team. And this team, in our case, should involve embryologists, it should involve administrators, it should involve somebody from your quality team as well. First, next step, we're going to review our existing processes and then sit down and brainstorm on potential failure modes at each step of the process. These steps, if you think they can be done incorrectly, they can be done incompletely, they can be delayed, or they can be completely omitted from the process. And it's important to note the failures or the potential effects of each failure. Next, we're going to rank those according to the severity of the failure. We're going to identify the likelihood of the occurrence. Is this something that's very rarely going to happen, or is it going to happen often? We're going to identify the probability of detection. Is this something I'm going to see right away? Is it going to be easy to identify before it happens? Or is this going to be really difficult and I'm not going to be able to see it coming? And we're going to calculate a risk priority number, or RPN. We'll go through that in a little bit. We're going to create an action plan. We'll monitor our success. And finally, we'll repeat the process. So if you look at this guy on the right, it's pretty simple. Don't do anything wrong today, don't do anything wrong tomorrow, and just repeat that day after day. So it's important that this be given the respectable amount of time, and that's something that you can determine depending on the extent of the process you're gonna do. So as I mentioned, first we're going to rank the severity, frequency, and detectability of each failure mode. These are graded on a scale of 1 to 5, with 1 is the lowest score, which would be, in terms of severity, no injury, all the way up to a 5, where we would see permanent injury. The occurrence, how often might we see this happen? 1 is a very remote possibility, and 5 is a very high likelihood this is going to happen. And finally, detectability. How likely am I to identify this before it happens? we're a scale of 1 to 5, where 1 is a very high likelihood that I would see this coming, to a 5, which is a very low likelihood of detection. And so we can use these 3 factors to calculate the risk priority number, or the RPN. They're ranked according to severity, and a high is going to be a 5, 5, 5 in each of them for a total score of 125. And the lowest is a 1, which would be a total of 1. I can do math, maybe not as well as Vicky can, but I can do that part. So the RPN score determines the priority of the failure mode. So the higher the score, the greatest need for our intervention, the most critical the need. And we need to set a threshold for critical, and that's going to be independent to our own clinics and our own laboratory. So when we reach that score, this particular failure needs critical attention. And then we direct corrective actions specifically to reduce the risk. We may not be able to make the risk go away, but we can direct our actions to reduce that risk. And we need to set a time frame and measure the RPNs before and after that time frame. And depending on what you select, that time frame could be a period of, as little as a month, it could be a year, but it's important that we look at it before and after so we can evaluate our progress. In addition, this RPN should be evaluated and performed by the same team for consistency's sake. Okay, well, this is well and interesting, but what does this have to do with me in the IVF lab? Why should I be concerned about this? Well, when you think about what we do in the IVF lab every day, it involves quite a high degree of complexity. We have multiple processes that are occurring simultaneously. You've got egg retrievals and sperm preps and embryo transfers and freezing, thawing, biopsy, tubing, all that going on all at the same time, most every day for a lot of us. We have multiple operators involved with the same patient, and those operators have different skill levels and different training levels. And so we can see failure in any number of areas, including equipment, record keeping and documentation, a failure to follow protocols, lack of training, and finally the laboratory environment itself. So interest group in Milan studied the IVF process in their laboratory and conducted an FMEA and broke out a typical IVF cycle, as you see here on the slide. So we've got an egg retrieval and sperm preparation that we use for IVF or ICSI. But don't forget that the patient may be freezing some of those sperm or embryos here. Sperm or eggs, introducing gamete cryopreservation into this first step. So we're going to freeze, or we're going to inseminate our eggs, but don't forget that patient could also be using frozen sperm or frozen eggs, thus introducing a thawing step in here as well. Once we've got our fertilized eggs, we're culturing the embryos. We may choose to do an embryo transfer. We may choose to do a frozen embryo transfer with that, introducing another thawing step. We may do a freeze-all cycle with no embryo transfer. We may do an embryo biopsy, which then will have a cryopreservation step, and we have a tubing step in there as well. So this is a basic IVF cycle that we do in the lab today, and you can see how involved this can be. And so what their group did was they identified those 11 main processes that we saw on the previous slide, and in those processes, they identified 68 different potential failure modes and effects. 68, that's a lot. They segregated those into 5 dominant groups, and you'll see those below here, samples that could be mismatched, lost, damaged, contaminated, and our inability to trace where those gametes went. And this table shows how they broke out their rating of the scoring system of 1 to 5, and we see the severity, occurrence, and detectability. So with regard to their IVF steps, a score of 1 was no injury to the gametes or embryos or the patients, all the way up to a 5, where there was permanent effect on gametes and embryos and potential mismatch. And the occurrence, they graded a score of 1 for a remote likelihood of this failure to occur. So less than 1 in 10,000 IVF cycles. down to a 5, which is very high likelihood of failure in 1 out of 20 cycles. And finally, the detectability, where a score of 1, very high likelihood they would have been able to detect this, down to a score of 5, which is a very unlikely chance of detection, or around 1%. And this is an example of just one item that they selected from their FMEA. They selected the potential patient mismatch at retrieval, sperm prep, or transfer. And the cause of this was they attributed it to incorrect labeling due to a human error, but the effect potentially huge, gamete-embryo mismatch. They assigned it a score of 25, and for their corrective action, they proposed a new witnessing step where they specifically directly asked the patient for their name rather than relying on it coming from another person. In addition, they had the patients sign their own labels for their egg retrieval and their cycle information. And when they reanalyzed it, they had reduced the risk pretty significantly down to a total score of 5. It's important to note that the risk needs to be assessed by each lab. So what I might find a risky process in my laboratory, you might not find in yours, and vice versa. So when we're facing a potential failure mode, we need to look at it as it relates to our particular practice. So we look at the number of cycles performed, the staffing level and skill level of the staff in the laboratory, the size of the laboratory itself, the equipment and supplies that we have available, and the work schedule. And those are all going to come into play when we're designing our FMEA. There are a couple of other papers that I will provide the references at the end of this presentation, but they looked at FMEA risks in the IVF lab. And these are really, really great papers to take a look at. Traceability of gametes during an IVF cycle in a single center as well as a multi-center. And if you can imagine how challenging this would be doing it in your own center, think about doing it across multiple centers. They also looked at witnessing protocols to ensure traceability during PGD, PGS cycles, which we know there's multiple steps in there that provide challenges for us. And most recently, assessment and management of COVID infection in the IVF lab. What can we do in the lab to reduce risk? And it's important to note that all 3 of these studies demonstrated positive change in reducing the risk in the respective IVF labs. So we're all aware of a number of situations that have occurred in the last few years, which have really exposed the vulnerabilities that we have when we are doing cryopreservation in the laboratory, whether it's sperm, eggs, embryos. And it's really time that we take a hard look at those and address that. So I just did this little brain dump, and I don't expect you to be able to read this because we're going to go into more detail in a couple of minutes, but literally I wrote these down in 2 minutes. I could come up with 15 or 20 areas where we are at risk when we're freezing and thawing. It's pretty frightening when you think about it. So I divided these into 6 categories, the first of which is technical, then equipment and supplies, quality management, monitoring, documentation, and finally shipping and receiving. So what are some of the steps that we need to be focused on in technical? Are we following our SOPs? Do we really look at our procedures? Do they reflect what we do? Are they updated on a regular basis? We all know you need mad pipetting skills to be really great at freezing and thawing, and you can't underestimate the importance of that. Capping and uncupping. Vicki did a great job talking about the different cryo devices and the risk that we're putting our gametes and embryos at, but just by the simple act of freezing and thawing. She talked a lot about this innocent exposure that occurs when we're, again, capping and uncapping, doing ID checks, doing inventory checks, moving them into the nitrogen after freezing, taking them out of the nitrogen when we're thawing. These little innocent exposures to temperature fluctuations can add up. There may be unknown damage throughout the procedure that we're not even aware of. There's some risk of contamination, and I think Martine's going to talk about some of that in the lecture to follow this one. Contamination can come from the operator, from the supplies, from the media, from the air, and potentially even from the liquid nitrogen. And One important step, especially for oocytes, is the interval to cryopreservation. Are we keeping that time tight? And enough studies have shown that that interval does matter. So we need to be really careful with that. With regard to equipment and supplies, we need to be purchasing high quality equipment and supplies and make sure they're consistent, make sure they're tested for toxicity. Are we using them as they were designed? Are we using them properly? And for many of us in the United States, supply chain interruption has been a huge factor. As recently as last week, we had a challenge buying cryo tanks. So no matter what kind of supplies we have, if we don't have a tank to put them in. And so we need to be open to looking at different devices, different media, different supplies, but again, they all need to be tested. So these are all challenges we face with regard to equipment. Monitoring quality is one of the things I think is most important. And in my opinion, instilling the value and importance of quality management to all staff is the utmost importance. And you need to avoid complacency. People need to understand why they do their QC checks in the morning, why it's important to follow up with those. We need to monitor the laboratory environment, the temperature of the media, the temperature of the oil, the temperature of the room, the temperature of the hood that it's sitting on. Is the airflow, is it on, is it off, is it filtered? Do you do it in a hood or not? Are we using appropriate culture medium for what we're doing? Are we using the appropriate gas? And are we monitoring our KPIs? It's really critical to look at all aspects of freezing and thawing. For example, when we're looking at our KPIs for freezing and thawing after biopsy, we look at the biopsy tech. We don't just do pregnancy rate and survival rate. We do a lot of biopsy in our practice, and we want to make sure that each person biopsying is not damaging the embryos. So we actually look at survival rate and pregnancy rate even by biopsy technician. Alarms obviously is a huge factor. Do you have alarms? Are they monitored? Do the people know what to do to respond to the alarms? Are they updated? If you've got 3 new tanks, did you get new alarms for those tanks? And finally, emergency plan, which obviously can be a huge project unto itself. Are you prepared for earthquake, fire, hurricanes, those kinds of things? And as we get bigger with more tanks, bigger centers, that becomes a big challenge. I think documentation is also really critical. We need to look at our labeling systems, missing documentation. Are we following the patient's treatment plan? For example, if the patient has 20 embryos, but they only wanted to biopsy 8, did we pay attention? Did they want to do biopsy? Are we going to the right lab or not? This is all part of the patient's treatment plan that we need to follow carefully. Consent forms obviously goes without saying how important that is. Are both partners as applicable on the consent forms? Do they understand what they're consenting to? What are we doing with their aneuploid embryos if they have no euploid embryos after their cycle? And finally, the storage agreement. Do they understand that you may not store the embryos forever? Do you store aneuploid embryos? Do you require them to do long-term offsite storage? So it's really important that those steps are included in this. Shipping and receiving. In our practice, we always say, it's better to bring the uterus to the embryos than the embryos to the uterus, but that's not always possible. So are we following strict protocols? Do we have all the infectious disease testing in place and any FDA labeling that might be required to ensure that your SOR is accurate and up to date? Tank control, unless it's our own tanks that we're shipping and receiving, we're putting a lot of trust in the courier that those tanks are checked for hold time, that they're stable, that they're not damaged. And then the transfer in and out, when our Vicki mentioned this a little bit briefly in her talk about transferring the embryos or gametes in and out of your clinic. And it really should only be a very highly trained person that is doing that, because there's a lot of potential risk for this innocent exposure at that point. So in summary, the FMEA is a proactive tool for risk mitigation. It utilizes a team approach, engages a number of different areas of the practice. that failure modes and the risk priority number should be evaluated both before and after implementation of this procedure. And frightening to say that cryopreservation provides us endless opportunities to evaluate and mitigate risk. And I think we all need to take a good hard look at this in our own programs and get busy with it. This summarizes a little bit. This seems like a little bit of a backward approach maybe, but we all want progress. But if you're on the wrong road, progress means doing an about turn and walking back to the right road. And so in that case, the man who turns back soonest is the most progressive. There's a list of references. These are outstanding papers and other publications. I would highly recommend that you take a look at it. Everything is spelled out step by step, can help all of us identify which areas we're vulnerable in our own practice that we need to look at. So great information here. And thank you very much for this opportunity.
Thank you, Kristen. That was a fantastic talk. I know personally I'm excited to start working on that in my lab. I think it's interesting that it kind of gives a quantification score to these things that we you know have always seen as risks, but when you can quantify it, it really kind of itemizes it for the lab to to see what needs to be prioritized and addressed. Along those lines, how do you implement both the analysis of doing the actual exercise and then the corrective action as well? Do you break it up into sections like cryopreservation or patient identification? And then how do you get sort of buy-in from the staff?
Great question, or multiple questions in there.
Sorry.
I think the scale itself can be designed by your own laboratory. So it doesn't have to be 1 to 5. It can be 1 to 3, it can be 1 to 10. I think this is a long process. It's not something that you're going to get done in a couple of weeks. It might, it might take months and months and months. And so I think the first step is identifying where you feel the highest risk might be for your practice. And every group should have some sort of a quality management team, and that might be a place to start to bring it up. And I think if you introduce it as a positive tool and a risk mitigation tool, that it's a lot easier to proceed with it that way. Then doesn't seem quite so scary. It's like, hey, we're going to be proactive about this, and let's look at areas. So your question about where do you start? It's going to be different for different practices, and I think each group needs to look at it in their own way and figure out where they should start.
Right, that makes sense. Well, thank you very much. I'm sure there'll be lots of questions coming later.
Thank you.
Okay, so next on the docket, our next speaker is Dr. Martine Nijs. Martine is an ESHRE accredited senior embryologist and former lab director. She is the author of numerous peer-reviewed publications and book chapters, and has presented hundreds of lectures as an invited speaker at meetings worldwide. She has been actively involved in organizing international conferences, workshops, and one-to-one practical training. Martine is an ad hoc board member of 10 international journals and an active member of 8 professional societies. Martine is currently the global training manager at Cooper Surgical Fertility Solutions, and they have generously sponsored her presentation today, which is entitled Clean Dewars and Glass Houses. Martine?
Thank you so much, Alison, for your kind introduction, and as well, thank you to the International IVF Initiative for inviting me and giving me the opportunity to talk about this very sexy topic, cleaning in the laboratories. So let's get going. First, I have to disclose that I work for Cooper Surgical Fertility Solutions and that this talk is sponsored by the company as well. So, cryopreservation is, as we heard from the previous speakers, cryopreservation of gametes, embryos, and reproductive tissues is really an integral part and central part of our ART work these days. And all labs provide storage of an irreplaceable reproductive tissues, such as oocytes, embryos, and sperms, and ovarian tissue, testicular tissue. And this also includes tissues from cancer patients. So it is really, really important that these tissues must be maintained under stringent conditions, and quality management systems need to be in place for this storage as such. And luckily, we have great societies, we have governments that have produced excellent guidelines. There is room for improvement, there's room for more and more detailed information. We already have now a standard for ISO if you do transportation of cells. So we are getting there. We are getting guidelines for cryo storage. So we will be able to have best practice for safe and reliable storage of our gametes, embryos, and tissues. Now, how do we store? We store, everybody knows, and the first speaker talked in detail about this. We store at very low temperatures. And the basic product that we use is liquid nitrogen, and that is being produced by liquefying air and then fractional distillation. And that's a really industrial procedure. Having said this, there are now vessels that can do that themselves. So they are individual and standalone units that can store and produce a low temperature. It is colorless, it has a low viscosity liquid, and it is widely used as a coolant. We use it in our labs in a liquid form at the temperature of minus 196 degrees and at the vapor phase, which we hope that will be minus 150 degrees Celsius. So we need to do safe and reliable cryo storage. There are different types of cryo storage. There's the short-term cryo storage. This means that we will, like we heard in the previous lectures, we will take samples from the tank, bring it to the lab, and then warm them, or we are vitrifying samples and then have to bring them to our tank for long-term storage. For these, we use non-pressurized liquid nitrogen vessels, and most of them, they are in stainless steel. At least I hope you have these and not the cheap thermoses that you can buy in the supermarket, because we need to make sure that that temperature, that evaporation of liquid nitrogen, that boiling point stays as long as possible enclosed in that vessel. We also have our dry shippers, and these are very special. They're very light. Most of them are produced out of aluminium. And inside, we have a hydrophobic blanket consisting of synthetic amorphous silica and glass fibers. That's an absorbent product. So when we fill it up with liquid nitrogen, the liquid nitrogen will go into this absorbent blanket and it then will dry out, but the temperature will stay cool at hopefully minus 150 degrees Celsius. We use these for transport of samples. This could be within clinic, this could be between clinics, this could be, we could even ship them on an aeroplane, etc. So these are the shippers that we use for our transportation. The long-term storage, we also have different types of vessels, and you can see some examples here. The top one is the European Sperm Bank in Copenhagen. Very simple, basic, larger vessels on wheels so they can be moved, and they're manually filled there with liquid nitrogen. They are stable and checked every day if they have enough liquid nitrogen in them. And then on the left down, you can see from my previous clinic where I work, these are vapor phase and liquid nitrogen phase, larger storage tanks. And we really love them. Once you get used to working with them and you have defined the exact time, how long you can open them to ensure that the temperature doesn't change. These are great vessels to store samples, a large amount as well. On the right hand, you have an even more industrial style. This is from the Assisted Conception Unit in Dundee in the UK, where they have automated fillings and everything, and alarm systems as well. Of course, you need to bear in mind that we need separate storage for virus-positive patients, and for those, most of the time, we use the smaller full liquid nitrogen vessels. So, we are storing, but is there now a risk for contamination of those samples? And if so, how to prevent this? It is clearly when we produce the industrial way, when we produce liquid nitrogen, there is a very low microbial count during that production. But it's really during the storage that we have contamination. And also, the scary thing I found when I was scouting in the literature, it is the common cryoprotectants that we use that could be spills on straws, on vials. and this could be glycerol, DMSO, ethylene glycol, etc. They are also helping those bacteria and viruses to have no cryo injury. Also our media, for example, some components like serum or serum albumin, they will prevent cryo injury to those contaminants. So it is a little bit scary, but is it true? Do we have contamination? Let me show you first some examples from the, mainly from the bovine world. Yes, they found different bacterial and fungal species in their liquid nitrogen tanks. This is within semen tanks and embryo tanks. They also found in the human hematopoietic stem cells that there were 1.2% of the freezers had bacterial and fungal cultures. And this is really remarkable. This was in the liquid nitrogen. But there was another study, but this is also done in the bovine system, where what they found was in the crystals that were on the lids and the canisters and on the bottom and the sediments of the tank. There they found also bacteria and yeast species. There have been also some experimental work, and again, viral agents of animal origin could infect vitrified bovine embryos in an experimental setup. And then, of course, there is this horrible scenario when you clean the tank and you find all this debris at the bottom of the tank. And this is clearly, I've seen it in my labs. This is from a scientific paper in the animal world. So lots of stuff is in there. And that's not only straws or devices, but also even pens or scissors, etc. And again, from those debris and sediments, there is a high risk for infection, as you can see here by different studies where they found fungal and bacterial contamination. And also in the crystals on the lid of the Dewars. What about a vapor phase liquid nitrogen? Is there a risk for contamination? Well, here we have some examples of experimental setups where they exposed embryos and semen samples to previously contaminated shippers, and there was no cross-contamination of those embryos and semen samples. Also, they contaminated and they mixed contaminated and non-contaminated samples in an open container, so in a vapor phase, and again, there was no transmission. But in another study, they took culture samples, as you can see in the picture, of the vapor phase, and there were positive cultures for different bacteria and fungi. So there is a risk for these contaminants being present in your storage vessels. So what is the risk in the human situation? There is another study on mouse that is done by a Japanese group where they exposed the hepatitis virus in vitrification in cryotubes, and there was no cross-contamination. However, in the rabbit study, there you could see cross-contamination and cross-infection. So far in the human system, and this is a study from Kobo, they checked for HIV, HBV, and ACV. They could not detect the cross-contamination in their vessels for oocytes and embryos from those chronically infected patients. The only publication is on the human system is where there is a transmission of hepatitis B, and this is for cryostored bone marrow, where leaking bags contaminated other bags. So there is a theoretical risk, it seems, but we do know that if the embryo has a zona pellucida that is open, there is also a theoretical risk of these pathogens to enter near the cells of the embryo. And also that if there is an infection, this will clearly reduce the chance for a pregnancy and a healthy child. So how can who and what can be the sources of the contamination? These can be the patients, the donors, the operators, the materials, the equipment, liquid nitrogen, storage vessels, and also during the shipment of the cryopreserved samples. So let's have a look. Of course, for patients and donors, we have those great, good clinical and laboratory practices, guidelines, laws, and bylaws. So we need to use them to test our patients and our donors and use these quarantine storage vessels for virus-positive patients or for those patients for those we are waiting for the test results to come in. So in this way, we can reduce the risk for cross-contamination. What about materials and equipment? So I've listed here on the left, you can see the equipment that we use when we are working in vitrification or standard manipulations in the vessels and the Dewars. So we have the surfaces, we have our gloves, personal protective equipment, but also the small forceps, the goblets, the canes, the freezing devices or the heat sealing devices. These can be sources of contamination. And on the right hand, I've listed the GLP. So what can you do to prevent? Well, for the first two ones, the surfaces and your personal protective equipment, use the standard cleaning products from your lab. Forceps and also your canister goblets and canes, you can heat or gas sterilize them. And if you use a disinfectant, you have to clean them outside of the lab, because ethanol is the ideal product, but this is really toxic for your IVF and andrology environment. So you have to have a specific environment where you can do that cleaning. The devices for slow freezing and heat sealing, you really have to look at the supplier's guidelines. Standard, we would disinfect, we wipe it before we would use the heat sealer, and really make sure that we would do that before and after the use of the heat sealing device. What about the way we freeze sperm? Well, there have been a lot of studies, as you can see, and on the left are the different methods and devices used for freezing sperm. And the pellets has the highest risk because there it's an open vitrification, very fast, high-speed freezing process. And even if you put them in specific carriers or pooled straws, you will reduce the risk, but there has been an initial exposure to liquid nitrogen. Glass ampoules are safe because they're closed, but they can explode. So there is the risk for contamination, of course, also injury to yourself. And then there are the different types of straws. And I'm not going into the details, but the only one that is really solid is the ionomeric resin straw. That will not break, it will not melt. You can seal it, heat seal it, and it is also being impermeable to pathogenic agents. It's also FDA approved if that is really necessary where you are located. So the GLP here will be use those straws with heat sealing. Don't use the polyvinyl alcohols dipping and wiping, closing of the straws, but heat seal them, clean that heat sealing system before and after you've used it, and then disinfect the outside of the straw before the freezing and after the thawing. What about our vitrification devices? There are the open and the closed. So there is a contradiction, first of all, a hesitation to go for the closed devices, because it could be that the temperature, cooling and warming temperature are different, and they are. But it seems, and there are different studies and meta-analyses already out there, that there are conflicting data. So we have people who work with the open system with very good results, as well as with closed devices. So if you are working with these, either what the best advice is to avoid and to minimize the risk is that you serially wash your oocytes in embryos before you load them on the device, and also wash that device with sterile liquid nitrogen before you use it. You load the oocytes or the embryos on the device. Now, this sterilized liquid nitrogen, you can produce yourself. You can use a specific filter, or you can use UV exposure machine. It is not simple, it is not cheap, and it produces a low amount of liquid nitrogen. But if you have a risk population of patients, it might be a good way to prevent these potential contaminations on your cryo devices. And then you yourself, you can contaminate as well, you as the operator. So you need to do that very, very good, good laboratory practice. Be clean, work clean, decontaminate before and during and after, in between patients, etc. And also now in time of SARS-CoV-2, you have to wear these protective gloves. Well, use other gloves inside those large protective gloves so you will not contaminate your colleague. Also use electronic witnessing wherever possible, so you have staff distancing and you have we have a reduction in the contamination risk of the samples of the liquid nitrogen or the vapor phase. Of course, all this has to be done in safe environment. I'm not going into details on how you have to have the equipment and the room, etc. Now, how to clean those vessels? There is actually one golden rule: follow the supplier maintenance and cleaning instructions. Don't try to invent anything or by hearsay. Follow the supplier maintenance and cleaning instructions. They know their products, they know how it is composed, what are the metals, the plastics, etc. And they will advise you on what cleaning solution you have to use. Clean outside the IVF lab, not inside your lab. So when you bring the tanks, the vessels outside, you don't have the risk, and we are so strict in our IVF labs, and rightly so. We don't want VOCs, we don't want those toxicities in the air, so do that outside. Clean the vessel also outside, not only on the inside, but also on the outside. That is key. So this is the general, the golden rule, so to speak. If you have these smaller tanks, sorry, typically you would clean inside and outside with sterile water. You would spray or fill the vessel with the cleaning product. Then you will agitate the vessel so it really covers inside. You will empty the vessel and leave it to dry upside down. It really needs to be dry completely, because otherwise, if there is still water in there, this can form crystals when you add liquid nitrogen. Some units, they used swab to test, and the advice as well is for your daily use is to, after each opening, remove condensation from the lid with a sterile cloth. So then you don't have crystals that will drop into your tank. Of course, these larger vessels, that's an issue. That's really difficult to clean yourself. And you can have a contract with the supplier that they exchange these vessels. We had this, so they would bring a cleaned one, tip it up with liquid nitrogen. We would move all the samples with their help, and then they would take the larger vessel and have it cleaned. So again, when you open it on a daily use, remove the condensation from the lid with a sterile cloth. And then the dry shippers. This is a very nice paper from Alicani Parmigiani. Shows you what happens to a dry shipper when it is being moved by car, by taxi, by carrier plane. So there are many, many partners involved, and there is, there is a risk for contamination. So you have to have a really good system, clean outside when the shipper arrives with sterile water and disinfectant. Again, here, read what the supplier tells you to do, which cleaning product, and because here you will have the specific absorbent material that you could damage if you are using the incorrect cleaning product. Some will advise you to fill it up completely. Others will advise you to spray. So again, ask them for advice. Empty the shipper, leave it to dry upside down. Again, it needs to be completely dry before you start using it again. And weigh the shipper. This is systems that you can use to see if it is completely empty. Now, these days, there are also disposable dry shippers that can guarantee you a minus 150 degrees Celsius. So that might be an option if you don't do many shippings. It is not so eco-friendly, but at least you know you have a clean and a single-use cryo system, a shipper to be used. And replace the absorption material regularly. So we are very conservative. We forget that this gets damaged because we poke in there, we go in there, we put our canes in there, but remove that, change it every year. So then the question for sure that I will find in the Q&A box is, Martine, which product do we need to use? And this is a tricky one. And also it's not a tricky one. As I said, you have to clean outside the lab. That gives you some freedom to use and choose your cleaning products. ask the supplier what works for this specific shipper, because some products can be corrosive if it's aluminium or steel. Some might damage the inner layer, so really ask their advice. And in this paper, there is an overview of what products there are available and that were tested, and then also if there was a decontamination, so they did microbial tests, and also what the practical aspects were. So as you can see, there was lots of stuff going on, potential carcinogen, it caused the gel, so acrylic odor. So again, really choose that product wisely. So then to summarize, I think the quality management and good laboratory practice that is in place in your laboratory needs to guide you through these cleaning and safe cryopreservation and storage methods. So you have to assess, and we heard it from Kristen before, you have to assess the risk in your cryo storage system. What are the risks for contamination in my system? Not the one in the paper that I'm just reading, no, in your lab, in your cryo storage room. Follow the cleaning instructions from the manufacturer, develop your own SOP and train the operators, deep clean before you start using a vessel, validate or requalify. And as I said, daily use, remove those crystals and condensation with a sterile cloth. Clean when you start doing your procedures, clean before and at the end of the day, and also in between patients, and transport before and after transport. Follow your guidelines and treat each sample as if it is positive for contaminants. So then you will have this routine as well when you are faced with a sample that is contaminated. And have those samples split, quarantine tanks, depending on the pathogen, and wash away, reduce, dilute the risk, the contaminants in your oocytes and embryos when you are vitrifying them. And keep documentation. Traceability is key, of course, of all that you are doing. So the title of my presentation was Clean Dewars and Glasshouses. I'll leave you with this is the glasshouse or greenhouse from the Belgian King in Brussels, which is normally open for public in May, but unfortunately this year we will not be able to go in there, but hopefully next year you can come and visit and see all the beautiful flowers that are in this greenhouse in Brussels. So thank you, and I'll leave you as well with the references, and I'm open for questions. Thank you.
Martine, thank you so much for a really excellent lecture. You covered so many of the questions that I've had over the years that I haven't felt have been satisfactorily answered until now. So congratulations for a really superb presentation. Thank you. So we have several questions for you. Let me pick one. Okay, this is from an anonymous attendee. Has anyone ever reported negative impact on cryopreserved specimens if the cryo tanks were not cleaned?
Reported in the sense in a publication, or reported to the health authority, or reported to a colleague?
I think anywhere.
Anywhere.
I guess the gist being, you know, are we angsting over something that's unnecessary to angst over? I think is really the gist of the question. Well,
I think the literature, we cannot find any evidence that there is cross-contamination in human ART. But I think also, if I compared what I found study-wise, the animal world has really focused much more on this when we compare it to our profession. So maybe we haven't investigated enough. Now, practically in my lab, as I said, we have cleaned the tank and we found the straw and we found debris. After we found in the literature about these contaminated crystals, we started cleaning the lids every day. There was a pile of sterile cloth, so it is a cost, but in a time, but people got used to it and they felt happy. Made the planned cleaning that we did every year much easier because you are much more in control. Yeah. So publicly, I think you hear from this, but I've checked also the serious adverse events registration from Europe this week, and I couldn't find any reports in the last 3 years on this.
Okay, thank you very much. So now, ladies and gentlemen, we're going to open the question and answer session. And my understanding is this will occupy the next 15 minutes or so. And so I will be asking a couple of questions and Alison will be asking a couple of questions. We'd very much like this to be sort of, in a way, didactic, if we can make it so on the virtual forum that we're at. A little bit tricky, but let's give it a go. So my first question is for you, Vicky. And this question is from Stephen Mullen. And he asks, have you tried to measure the critical warming rate of the vitrification solution commonly used for human oocyte vitrification?
If I try to measure with a thermocouple, I guess, I haven't been able to do it because they are just so small that I use the numerical methods. And what I did was when I numerically modeled things that I can't measure, but other people have measured, like Peter Masur, I used his data to insert in my model. So he made a very little thermocouple and measured in 0.1 microliters, but I don't have that equipment.
Fair enough, okay. Okay, this is a question for Kristen. And this question is from Meenakshi. I apologize if I'm not pronouncing your name correctly. Dev Chowdhury from India. And he is interested to know how to prepare for fire safety in a cryo storage facility.
That's a tough one because everybody's situation is different. If you're on the ground floor, if you've got 1 tank versus 50 tanks, I think one of the things that I would do would be to do an evacuation plan and see what your opportunities are for evacuating. It's going to be pretty impossible to evacuate 50 cryo tanks or 1 extremely large vapor tank. So, but I think look at evacuation routes that are potential. Look if there's an opportunity. If this is something, for example, we experience wildfires, threats in our areas, or you have an opportunity to move your cryopreserved samples to another place, a safe place away from the fire. I think it really, to start by just assessing your own situation and the resources that are around you. And also to keep in mind that if you're up on a higher floor in a building, you may not have power for the elevators. So I think, all of those things need to be taken into consideration.
Yeah, can I add to that? Because
yeah,
when we had a new build, we met up with the fire brigade and we made a plan. We had closed windows, so we had to have one window that we could open in case we were on the 2nd floor. We also prioritized tanks, so we labeled tanks that they needed to take up first. We split our samples over different tanks. We had extra sprinkling. And we had now it's all, these days it's all in the software, but the inventory of the tanks was in a separate place. So if the cryo storage would burn down, we would still know what was in it and the other way around. So it wouldn't, we were reducing the risk. And we had to train people also to do what and when and what is the risk. We had to train the fire brigade to work with nitrogen as well. So it is a whole project.
I think Martine's point of having duplicate or multiple inventories can't be emphasized enough. The importance of that, so regardless of what happens, at least what you had and where it was.
To your point, Martine, regarding splitting samples, though, of course, I think this is every embryologist's dream, just in case a tank explodes, for example, or you get severe contamination. I think the issue probably is, and I'd love you to address it, is that we are increasingly dealing with huge numbers of frozen specimens that we'll never use. And the maintenance of these specimens, let alone the cost of the tanks, is very considerable. And it does also add complexity to the inventorying if you have samples split across tanks. So I just wondered if you could sort of give your view of what you think is the best way of addressing this is a question I've really wrangled with myself.
Well, I think, and it's not only in Belgium, but here the government and the professional body were really proactive and had a vision. So what patients here have, they have full reimbursement for 6 cycles on the condition that they only get 1 embryo transfer. That means we'd have a lot of cryopreservation. But before they start a new fresh cycle, they need to take those frozen cryopreserved embryos back. So that means that you will always accumulate, but not as much as people who will keep on restarting with new cycles, etc. Also, there is restricted time on the storage. These conditions are all explained beforehand, etc. Except there are exceptions in case of disease, etc. But it is a problem. You're completely right. There is a huge amount of embryos that are in sperms and tissues, etc., that are being stored. And traceability is key. And it is a project. We had a course today, and one of the modules was on cryo management. It is a full-time job, actually, to follow up all those samples every day and plan and etc. Yeah.
Thank you. So Alison, do you have questions?
Yes. This next question is for Martine. It's from Iona Racowsky. I apologize if I did not say her last name correctly. She wants to know, how often do you clean your cryo tanks? And maybe if you could just expand upon what your implementation scheme strategy is in terms of managing the cleaning process.
Yeah, so when you start, you can't clean them all at once. So every month there was 1 tank that will be cleaned. We had also a person dedicated to this, trained to do that. We had an extra tank. And as I said, the big tanks, we had a contract with a company. They would come and bring a clean tank, fully tipped with liquid nitrogen. We could move, with their help, the samples quickly, and then they would take the big one and clean that. But every month there was, on a regular basis, a rota, like the incubators, every month. So someone was really dedicated to the cleaning. Yeah, and there's no other way. The other way is to do that during a holiday, for example, over Christmas and New Year. But then you need so many extra tanks. So to reduce the cost, and you need space as well to do that. As I said, do this outside.
Yeah,
you need to be able to move the samples and then bring the tank out.
My next question, again, about tanks, I think can go to everyone. What do the speakers feel about using tanks outside of the warranty? Because they all come with warranties. Would like your opinion. That was an anonymous one as well. Kristen?
Well, we have, I mean, coming from the animal science background, we know those tanks last and are functional almost indefinitely, as long as they're not abused. However, in our own practice, we did adopt guidelines, and we have switched them out after a certain number of years. So we do continue to buy new tanks because we're trying to do what good lab practice dictates, which is follow the manufacturer's instructions. So we have changed out all of our tanks, and we do have a lot of tanks. So it's an expensive venture, but we want to do everything we can.
Yeah, I think it's another point, like Catherine made, where somehow you have to balance this incredible cost and undertaking with following manufacturing guidelines.
Right.
Well, I think you can check the tank. You have to check the tanks every year as well, if they are still doing what they're supposed to do. If there's no leakage of visual, but also weighing and looking at how much nitrogen you need to use to fill it up, if there is a change over time, etc., etc. Yeah, there is the thing is, if something happens and you cannot demonstrate that it's still on the warranty, you have an issue. You have a problem.
Sure.
So
I agree. We look at our tanks. We measure them every day, which is a crazy amount of work. And so we do monitor the usage. But I agree with you, Martine, that if you are using them outside what the manufacturer recommends, I'm not sure that that, you know, measurement every day and looking at your usage is going to hold up for you.
But I guess that just to play devil's advocate, the million-dollar question really is, how often do these tanks explode? Then if you compare the old ones to the new, in my experience anyway, the ones that we receive in the US, it's like old cars. Old cars are so much better than new cars. The old tanks are so much more, they're so much more robust and better built. So, you know, it's tricky. I mean, certainly in the hospital I worked in Boston, Brigham and Women's Hospital, I was getting constant pushback when I asked for a new tank. Well, why do you need a new tank, Dr. Racowsky? You've got a whole line of tanks in your tank room. So
I don't think they will explode. I think there will be cracks and leaks.
Okay, well, yeah, become unserviceable. Because I'm being a bit dramatic. But.
Yeah, I understand what you wanted to make the picture. Yeah, but the only way to do is to check regular checks, especially with the dry shippers, because they're being moved around left and right. And as you nicely described, Kristen, you have no control once you hand them over to the courier. You hope that they know what they're doing, but you have no control at all. So checking and really being very critical.
Okay, it's my turn. So this question is for you, Vicky, and it is from Kelly Tillerman. And she basically says, I love your data and your paper. Have you done the following experiment and looked at temperatures? Straw in liquid nitrogen, straw to check for ID, and straw again in liquid nitrogen. What I mean is, can you find out if the sample is able to be solidified again without damage? Is there a timing and temperature that we must use, that we can use as a reference during manipulation? So this gets, you know, the freezing and the vitrification, the warming, and then deciding not to transfer the embryo or deciding we need to biopsy it and then put it back in.
She is using this procedure to check the ID of the person, of the sample, right? And
not necessarily, I think. I think what she's asking, well, yeah, actually, she did ask straw to check the ID. Yes.
Yes. Well, we try to do a critical time measurement through the numerical simulations, but I can't say for any cryoprotective solution what the TG is and how it can attain that TG. And also, as I said, you have a full tank or you have a half full tank, and it's different. And how to what distance do you uplift? Because you have a whole gradient of temperatures. So the lower it is, the better for the sample if you check it. But I don't, you can't really observe it until you thaw it or you warm it. Actually, if it's vitrified, you don't thaw, you warm, and you have to do that quickly. And unless you can see it survived, I don't know how else you can quantify that with experimental survival and time exposures like we did for each type of solution and for each temperature at which you put that sample to check the ID or to put in another tank or to do the activity you have to do when you uplift it above TG. You have to know the TG of that specific solution also.
Right.
Yeah, I agree with Vicky, but what we did was we validated the opening time of the big tank. How long can we open it until the temperature starts to increase, critical temperature? So it came around 5 minutes, so they had to close and then wait until it stabilized. And the second thing is we had a software where we saw the inventory of what was where. That doesn't mean you need to check what you're taking out of the tank. We also didn't store vitrified samples in the top layers, always lower, those tops would be empty. And we added extra in the vapor phase, we added extra liquid nitrogen because that had a bigger buffer for the vapor phase. This is how we worked. And electronic witnessing helps you as well.
Yes, I don't understand the part you said you have extra liquid nitrogen in the vapor.
The vapor phase has some liquid nitrogen in there in the bottom. And so we had continual alarm, so we increased that volume, and that was much more stable. But we checked how long we could open. We had temperature probes in the tank.
Where?
So that's how we identified the perfect opening timing.
The time lapse that it would be safe, maybe.
We think, but as you say, we don't know about that
Yes.
specific embryo on the device.
Yeah.
Mhm.
Okay, so this question is from Martine, and it is from Gulam Bahadur. And this person, I believe, is a man, but I'm not 100% sure. I'm so sorry. But you ask, what microbial culture should be done from samples of the sludge from the cryo tanks?
E. coli, this is what comes from the papers. If you look at you can see the presentation afterwards. E. coli pops up a lot, aspergillus, these things, yeah,
Okay.
unfortunately.
All right, thank you. Well, hopefully we won't see sludge anymore in our cryo tanks
No.
after learning how to maintain them properly.
But the papers from Bilansky are really, really good. So I recommend you read the most recent one. That's really great info. You have a nice overview of how and what about contamination.
Fantastic, thank you.
Thank you all so much. I think it is time to wrap up, although I think we could go on forever. We just wanted to thank everyone for taking the time to participate in this session and the lengthy discussion and heated discussion. It was fantastic. I particularly would like to thank the speakers, Vicky, Kristen, and Martine, and of course, my co-moderator, Professor Racowsky. Thank you to the organizing committee of this initiative, Jacques Cohen, Peter Nijs, Giles Palmer, Thomas Elliott, Shaista Sadruddin, and Marianne Savetes. Today's question and answer team, we're working very hard behind the scenes, pulling in all of your questions and organizing them into a very neat document for us. And so big thank you to Shaista and Marianne for that.
So thank you so much, Alison. So just as a reminder to all our attendees, our next session, which will be at the same time and same place, but on May the 4th, is entitled The Metrics. So top performing clinics will discuss best practices in oocyte collection and embryo transfers, which this session will be sponsored by Cook. And then there will be a unique look at an embryo transfer simulator for training purposes, which is sponsored by the ASRM. So we all very much hope to see you at the next session, and thank you so much for joining us this evening. Good night.
Bye-bye.